So here's a few examples to consider. The question is, for each of these, determine whether the series converges or diverges. And I want to take the approach like you see this series on an exam over series, and you're supposed to determine which test that you should use. So starting with this one. Since this is so close to a p-series, if we cover up the 1 here, we can express the cube root of n squared as into the 2/3 power, the old power over root rule for expressions like that. And so 1 over n to the 2/3, that's a p-series. So I would know from there, at least, I want to compare this one way or another. I want to compare it to the series 1 over the cube root of n squared, which is equal to 1 over n to the 2/3 power. Okay. Which is a p-series with p equal to 2/3, which is less than 1, so the series diverges. So the series that we're comparing it to diverges. If you try direct comparison test, which is a reasonable thing to try to begin with here, then here's the given terms, cube root of n squared plus 1 compared to 1 over the cube root of n squared. Bigger denominator here means smaller fraction. Now I'm going to draw that picture that I like to draw. So if I'm doing direct comparison test, I need to draw a quick picture. I have a larger series that diverges. That means that the partial sums for this larger series are increasing without bound. We know they're increasing. Diverges tells me they're unbounded. Well, then when I'm comparing to a smaller series, that's inconclusive. This is another case where, okay, so what does that say about the series underneath? And the answer is nothing really. I mean, it might converge, it might level off and approach some finite number, it might just increase without bound. I don't know which one it does. This is inconclusive. Direct comparison test, and this is another case where direct comparison test is inconclusive. So, now that you know about the limit comparison test, you might switch to that. And that's what I'm going to do. So I'm going to erase this. I'm going to keep the compare to this particular series plan, but I'm going to switch over since the comparison went the wrong way. It just didn't work out the way we wanted it to. Then we'll switch over to LCT. Now you have a plan B, now that you've learned about that. So we can take the limit as n approaches infinity of the terms in this given series, take the ratio of that to the terms in your comparison series, which is 1 over the cube root of n squared. So here I would move this up, multiply by the reciprocal. So this is 1 over cube root of n squared plus 1 times reciprocal cube root of n squared over 1. Since I've got cube root in the top and bottom, I can write that as one big cube root of just n squared times 1 on top, and then n squared plus 1 times 1 on the bottom. Because the cube root is a continuous function, I can kind of move the limit inside here. And inside, I've got rational expression, same degree in the numerator and denominator. So I use the ratio of the leading coefficients. So that's 1 over 1. So the limit inside here is approaching 1. Cube root of 1 is 1. So the overall limit here is 1. Now, what's important about this number is just really that it's a number. I mean, that it's finite. So with limit comparison tests, you just need your limit to end up being a finite positive number. But because we're taking a ratio of, terms with positive expressions, it's kind of guaranteed to be positive. So we just need it to be finite. That brings to mind, though, remember, you can only apply comparison tests if all the terms in your series are positive. Which, notice, for any value of n, this is a positive. This is going to give you positive terms. So when you get a finite number here, limit comparison test tells us then both series behave the same way. So since we're comparing to a divergent p-series, then by limit comparison test, this series must also diverge. So this series in A here diverges by limit comparison test with, and I know I've run myself out of room, but the 1 over n to the 2/3. Guess I'll write it here. 1 over n to the 2/3. So there's your complete answer. I know I've said a lot about in these videos about complete answers. If it's a comparison test, you have to say what you're comparing it to. Okay, and show the limit. I mean, make sure you show your work, but this is essential information. That's part of your answer. Okay, so that's A. B. So here's where you should really jump straight to limit comparison test. When you have something really messy like this, then the default choice should be limit comparison test, where you compare it to, so you take dominating terms in the numerator and denominator. So in the numerator, your dominating term is the n squared. As n approaches infinity, this n squared is going to get much, much bigger than the 3n. So the n squared is going to take over in the numerator as n approaches infinity. And the square root of n to the 7th is going to take over in the denominator. The 5n squared is going to become insignificant by comparison as n approaches infinity. So this is what we want to compare to. Now you should simplify that to help us determine whether this series converges or diverges. So this is n squared. I can express that denominator as n to the 7/2. And so then I can reduce that. So the second power here is the 4/2 power. So that's going to cancel out, right? And leave. So if I take away 4/2, I'm left with 3/2 in the denominator. So this is a p series with p equal to 3/2. Since p is greater than 1, this p series converges. So we're comparing it to a convergent p series. Limit comparison test. So we take the limits as n approaches infinity of the ratio of the given terms here, very messy, over our comparison series. You can use the simplified version or not. I guess I'm going to use the unsimplified version in this case. So n squared over the square root of n to the 7th. Say I write it that way, the way I wrote it to start off with there. Okay, then get rid of this to save myself some space and just make a note that we figured out that this is a convergent p series because p was equal to 3/2. Okay. So over here, limits n approaches infinity. This whole fraction was in the numerator. Multiplied by square root of n to the 7th over n squared. Okay, I'm going to take advantage of a couple of properties of limits. So I'm going to gather my square root terms and write it under one big radical. So I've got the square root of n to the 7th in the numerator, and then n to the 7th plus 5n squared in the denominator, right? And then times, so I'm collecting these terms. I'm going to put those in one limit, and then times the limit as n approaches infinity of n squared plus 3n all over n squared. Is that good? So now I'm collecting these guys. And with limits, the product of the limits is equal to the limit of the product. Right? You can with products, with limits, be careful, because not with derivatives or antiderivatives, but with limits, you are allowed to take the limit of one part of a product at a time. Here, so this limit right here, you have a rational expression, same degree in the numerator and denominator. So the limit is the ratio of the leading coefficients, which is 1 over 1. So this limit is approaching 1. This limit over here, square root is a continuous function, so I can move the limit underneath here. And the limit of this rational expression underneath, I got, again, rational expression, same degree numerator and denominator. Limit is the ratio of the leading coefficients, which is 1 over 1. So the limit in here is 1, and the square root of 1 is 1. So just this limit is also approaching 1. So overall limit, I have 1 times 1. This limit's approaching 1. Okay. So that's just grouping, again, take the limit of this part, it's approaching 1, and then take the limit of, I don't know if that's showing up, not very well, sorry. Okay, but so this limit turns out is 1, which means, so we got a finite number, both series behave the same way, since we're comparing it to a convergent series. So you have to go back and check, what am I comparing it to? This time we're comparing it to a convergent series, so the conclusion in for B here is that it converges by limit comparison test with that. This guy converges. Again, because we're comparing it to a convergent series. This one diverged because we compared it to a divergent series. Okay, or the conclusion was that it diverged because we compared it to a divergent series. Okay, last one, C over there, which is a bit of a mess. I think I'll copy it. In fact, I'm going to get rid of all this stuff. We've answered A and B. So thoughts about C. The sum from 1 to infinity of n times 2 to the n. So again, this one's a bit of a mess. These series that have really messy terms like this, that's prime candidates for limit comparison test, where you try to strip away the extra stuff, focus on just the dominating terms. So dominating term, well, the whole numerator's dominating, I guess. It's all one term in the numerator. Denominator, the 4n cubed dominates. Okay, well, then we could reduce that at least. Oops. To this. Now, we weren't as fortunate this time. This didn't just automatically reduce to a p-series or a geometric series this time. That's not either one. It's like, looks like a mixture, right? This looks geometric, this looks like a p-series. But it's not either one then. You can't mix them together and call it both or anything like that. So now we have some question. Okay, does that converge or diverge? Thing to notice here, that numerator is increasing a lot more quickly than the denominator, right? Exponential functions are among your fastest category, fastest growing functions. So limit as n approaches infinity, this is 2 to the n is going to take off and leave 4n squared in the dust. And so that ratio is going to approach infinity. To prove that, here I'll write it out. So we're taking the limit as n approaches infinity of 2 to the n over 4n squared. It's got the form infinity over infinity. You could use L'Hopital's rule. Derivative of the top is natural log of 2 times 2 to the n. Derivative of the bottom would be 8 times n. Still has the form infinity over infinity. If you apply L'Hopital's rule again, so now at this point, natural log of 2, this natural log of 2 is just a constant coefficient. So I just write that down. And then the derivative of 2 to the n is natural log of 2 times 2 to the n. Over derivative of the bottom is 8. Limit as n approaches infinity. Now this numerator is approaching infinity, and the denominator is just 8. Well, that's going to infinity then, overall. What's important about that is it's not approaching 0. So that's what I was saying earlier, why I was pointing out, hey, this numerator is growing a lot faster. This ratio is not going to 0, which means it diverges. This series diverges by nth term test. Now, it is true. I'm going to go ahead and admit this series also diverges by nth term test. So you could start off with nth term test right off the bat. But I encourage you to try that if you're feeling like, why didn't we do that? Go ahead and try it and you'll see why we didn't do that. This limit gets if you take the limit of this guy directly, it gets a little ugly. So you are actually better off taking limit comparison tests, make your terms in your series a little simpler. It's simpler here to show, okay, yeah, that definitely approaches infinity, so it diverges by the nth term test if the limit's not approaching 0. So if we know this series diverges by nth term test, we still need to tie that into our given series. So I still, unfortunately, have to deal with the limit as n approaches infinity of the terms in the given series over the terms in the comparison series. I'll write the simplified form this time. 2 to the n over 4n squared. Okay, so bring this up, multiply by the reciprocal. 4n cubed plus 6n times, so I have 4n squared over 2n. So 2 to the n. So the 2 to the n's go away. That's a relief, right? Because that was the nastiest part of this problem. And now we've got the limit as n approaches infinity of n times 4n squared, so that's 4n cubed, over 4n cubed plus 6n. So again, see how often, I think I told you guys, you'd see these limits often. Rational expression, same degree numerator and denominator. The limit is the ratio of the leading coefficients, which is 1. Positive finite number for your limit means both series, both the given series and our comparison series, have the same behavior. So since we're comparing it to a divergent series, the conclusion this time is that this series diverges by limit comparison test with the series 2 to the n over 4n squared. There's your answer.